Welcome to new and returning viewers to Juddy Productions. In today's video we'll be looking at a Unit 3 physics concept of oblique projectile motion. And in this particular example we'll be looking at an object that is elevated 40 meters above the ground, is projected at an angle of 60 degrees, and eventually strikes the ground. We're using an initial velocity of 25 meters per second, and we'll be performing a range of different calculations associated with this particular projectile motion scenario. We're being asked to calculate the following quantities. First of all, the maximum height above the ground. We want to know how far above the ground is the projectile at its maximum height. Number two, the time the projectile is in motion. So this represents the total time from the starting position all the way down to the ground. Number three, the range of the projectile. So here we're looking at how far across in the horizontal the object travels in total. And finally, the impact velocity of the projectile. So when the object reaches the ground, we want to know what is the value of the velocity of this projectile. So let's jump straight into it. In this question, we're asked to calculate the height above the ground that the projectile gets to, the maximum height. So we're really looking at the vertical component of displacement here. And of course the maximum height is 40 plus whatever the peak height is of the projection above the horizontal. So we'd like to focus on that and work that out first of all. So there we have it. Maximum height equals the 40 meters of elevation plus whatever height it reaches in the projection. Now to calculate that, we'll need to analyse the vertical motion of this projection. We're considering only the vertical component of this 25 meters per second, and we're going to calculate that by using the sine function of 60. So in the vertical direction, we have the initial component of the 25 meters per second. We've got the acceleration going downwards at 9.8 meters per second, and that's in the opposite direction to the displacement. The upwards motion is the initial direction. We'll take that as positive. So downwards being acceleration will be negative. The final velocity vertically right at the top will be 0. And we want to work out what is the vertical displacement. So let's use our Subat equations to solve this. So there we have it. Using the v squared equals u squared plus 2as, the final velocity at the top in the vertical component will be 0. The initial velocity in the vertical component will be the sine 60 of 25. The acceleration is negative 9.8 meters per second, and displacement is what we're trying to calculate. We simplify this. Our sine 60 of 25 gives us the value of 21.65, and two lots of 9.8 give us 19.6. The negative becomes our minus here. Then we're simply added this across to the left-hand side. So I've got 19.6s equals 21.65 squared. Divide both sides by 19.6 and we find the displacement above this horizontal location to be 23.91 meters. So to find our final height, the ball will reach a maximum height above the ground of 63.91 meters. In this second question, we're asked to calculate the total time it takes for the projectile to move from point A to point D, from the start of the projection right to the end. Now there are multiple ways to approach this problem. We could, for example, work out the time from A straight to D in one hit. However, if you follow that through, you end up with a quadratic equation that's quite challenging. Our second option is we could work out the time from A to B, and then the time all the way down from B to D. Because we're using the velocity vertical, acceleration vertical, displacements vertical to work out the time. So all this is going to be calculated using vertical information. So again, time from A to D in one hit is challenging because it's a quadratic equation. Time from A to B and then straight from B to D is another option. Or some students will choose to go from A to C and then from C to D. You can't do it in one easy calculation, so we need to break it up. It's a lot easier that way. My preference for today is to look at time from A to B and then from B directly to D in the next step. Let's try that. Okay, we'll break this into two steps. The first is to work out the time from point A to point B, and the second is to work out from B all the way down to D. Remembering, we're just looking at the vertical components. So let's work out, first of all, our time from point A to point B in the vertical direction. So here we have our variables. We're taking vertically upwards as positive. So the initial velocity in a vertical component, 25 times sine of 60, gives us a value of 21.65 meters per second. Acceleration in the vertical is downward, so it's negative 9.8 meters per second. At point B, right at the top, our vertical velocity reaches a value of 0, and we want to work out what t is. So let's now use our Suvat equations. Okay, so our first part of our calculation is the time from point A to point B in the vertical direction. We find that the initial velocity was 21.65, the final velocity was 0, the acceleration is negative 9.8 times t, and t is our unknown. So we transfer our negative 9.8t to the left-hand side as a positive 9.8t, and we divide both sides by 9.8. That gives us a time of 2.21 seconds from point A to point B. Now we need to add to that the time it takes for the object to drop from point B all the way down to point D in the vertical direction. So let's write down our variables. So vertically, dropping from point B all the way down to the ground, point D, we have an initial velocity of 0. We take the direction of the motion downwards as positive, so we now have an acceleration of 9.8 meters per second. Our total displacement from part 1 of the question was 63.91 meters from the top all the way down to the ground, and we want to work out what our time is. So let's now use our Suvat equations. Okay, so the time from point B at the top of the projection all the way down to point D in the vertical direction is 3.61 seconds. So the total time of this projection is the time from A to B plus the time from B to D. Let's work that out. So the total time for the object to project at 25 meters per second at an angle of 60 degrees, elevated by 40 meters to reach the bottom, will be 5.82 seconds. We're now asked to calculate the range of the projection. Now the range is in the horizontal. So first of all, let's consider this as a horizontal calculation. So horizontally, we have a constant sideways velocity. There is no acceleration. And we know that this particular projection took a total time of 5.82 seconds. So our displacement horizontally is the question. Our velocity, our constant velocity or speed horizontally is 25 cos of 60. And the time of this particular duration is 5.82 seconds. There is no acceleration in the horizontal direction, so we don't need to worry about the Suvats. We can use the simple displacement equals velocity times time. Now cosine of 60 is equal to a half, so that can be further simplified. So an object with an elevation of 40 meters, a velocity of 25 meters per second, inclined at an angle of 60 degrees, will have a range or a horizontal displacement of 72.75 meters. Okay, our final question asks us to calculate the impact velocity. So our projectile has shot and impacted the ground. Upon the impact, we have a horizontal velocity of 12.5 meters per second. In fact, that's the horizontal component of the velocity everywhere in this projection from this object. It's a constant, 12.5. It comes from the initial velocity, 25 meters per second, multiplied by the cosine of the angle 60, 12.5 meters per second. What we don't know is the final velocity as it impacts in the vertical. Now we could label that as a velocity in the y direction, or if you like, a vertical velocity. So in order to add these two as a vector to find the overall impact velocity, we need to first of all discover what is the impact velocity in the vertical direction. So let's now consider the entire projection. So for the entire projection, we have an initial vertical velocity of 21.65 meters per second, an acceleration opposing that of negative 9.8 meters per second squared, a displacement from start to finish of negative 40, and we want to know the final velocity, the impact velocity in the vertical direction. Let's now use our Suvat equations. So we find this object has an impact velocity just before it strikes the ground of 35.39 meters per second. So now we need to take these two values and add them together as a vector. Let's now do a vector addition of these two velocities. We've got a horizontal velocity of 12.5 meters per second upon impact, and we have a vertical velocity 35.39 meters per second. Here it is as a vector addition. We draw our first vector, the horizontal velocity of 12.5 meters per second, and at the end of that we add our vertical velocity of 35.39 meters per second. Now this is a nice right angled triangle. Accordingly, we can use Pythagoras' theorem, which states the large diagonal side squared is equal to side 1 squared plus side 2 squared. So let's sub our values in and solve for the unknown value of v, the final impact velocity. So the impact velocity at this point, heading in this direction, is 37.53 meters per second.